Welcome to Jazan University Laboratory Research Lab of ultra-low-level quantum measurements. I am Dr. Masroor Bukhari, Lab Director and Principal Investigator of this laboratory. This is just a brief overview of this lab for my students and anybody who's interested in low-level electromagnetic measurements. So what you see in front of you is essentially a Faraday cage where you have this shielding, this really high-level shielding which eliminates, not completely, but reduces all the electromagnetic interference from outside. And this sort of chamber is known as a Faraday cage. So this Faraday cage houses the main experiment, which is cooled to a temperature of about 77 Kelvin, which is a liquid nitrogen temperature, about minus 225 degrees, obtained with the help of a liquid nitrogen cryostat system, and you have this liquid nitrogen dewar where the liquid nitrogen comes. So this dewar or dewar stores liquid nitrogen, which is required for our experiments. The main element of our experiments is a cavity, an RF cavity. It is known as a radio frequency cavity. These are high quality, oxygen-free, 99.99% copper cavities. Right now it's wrapped in aluminum. And this cavity is where we try to house a sample, or simply once we are trying to eavesdrop on vacuum. So this is the cavity which is the center of our experiment. And this cavity goes into this, there's a cryostat, and the cavity sits inside, and then it's covered and filled up with liquid nitrogen. And there you have a detector which senses all the photons or these electromagnetic radiation which is present in the cavity as a result of external interference or without any external interference. And then coupled to that, this cavity is a weakly coupled antenna. I've been using tuning fork antennas. And then there is a detector, and then we try to measure that resonance. So basically you're trying to measure a very, very weak signal which is coming out of vacuum, coming out of quantum vacuum, and then you transfer it, try to detect it with the help of a detection system. So the first stage, because it's very weak, you have an amplification stage, and where I've devised a sensing and routing hub, which uses one of the foremost technologies like squids and things like those to measure these very, very low signals. So you have then a tunnel diode stage, you have a low noise amplification stage, and then it goes to a RF detection system. What you see here, this black box, which is literally a black box, is the workhorse for this measurement, which has the tunnel detector, the squid assembly, and then an RF detector. So all this then tries to generate a signal, and you have a bias circuitry that provides a very, very high precision voltage bias, which is required to maintain these. And then you have the signal coming in from a very ultra low distortion signal generator, which sort of generates the synchronization signal for this. So the technique that we use here is known as phase sensitive detection. What we do is that you have a very weak signal, which is also very noisy. So you try to generate a signal, and using that signal, you sync it, you try to lock in to that frequency that you are generating, which is basically a carrier frequency, 150 kilohertz or 200 kilohertz, up to 1 megahertz. And then you have a device known as a lock-in amplifier, and this is one of the latest high precision lock-in amplifiers from Stanford research. It was the first model, this newest model once it came, and at that time I got it, and it's a 2 megahertz DSP lock-in amplifier. So then you can find, using this lock-in scheme, this phase sensitive detection, you can find the amplitude and the phase of the signal that you're trying to measure. Then comes the stage of data acquisition, and then this is for calibration purposes. This is a RF signal generator up to 3 gigahertz, which generates the interference signal to activate vacuum or stimulate vacuum, or which is used for calibration purposes. And then you have a spectrum analyzer, Now, spectrum analyzers used to be pretty big when I was a student, but now they are computer-based devices like this one, which is from Aronia, a 6 gigahertz spectrum analyzer, which works with a computer. Then comes a stage of, so this Aronia spectrum analyzer is used for calibration purposes, and that sort of completes the setup. And then the signal, this analog signal, is delivered or conveyed to a data acquisition stage. So you see here this measurement computing data acquisition system, and then there's another one which is logged in this, in this another black box where it's trying to minimize all the external interference, and then the signal comes from there, and a parallel signal from there, from this T, goes to a digital storage oscilloscope from Agilent. We are fortunate to have one of the most highest possible standard instrumentation here as used in scientific research, because precision and accuracy are the most important elements of a measurement. And what we are trying to do is a measurement here. So this is used for calibration purposes. And then we have a system similar to LabVIEW, where you actually see the signal that you're measuring from the cavity in time domain and in frequency domain. So you can see the two peaks. What you see here is everything is just simple Johnson noise. And what you see here, these two peaks are actually your carrier signal at 150 kilohertz, and its first or second harmonics. So that's how you actually see a signal. And then you archive it to hard disk, and then you have analysis software with the help of which you do analysis and do these experiments. So this is what the instrumentation side we have. And then we have, in my lab, wherever I go, normally I try to establish an electronics lab for developing, assembling circuits or things. So we have a workbench here, which is where we have an assembly facility, even surface mount devices I've been making, because some of the instrumentation that you need is especially once you're working with very high frequencies. The frequencies we work with are gigahertz frequencies, around 3 gigahertz, 2.7 gigahertz, and we have to build cavities for those frequencies, and we have these copper cavities, as I showed you before. This one is for like 5.4 gigahertz. These are for 2.7 or 2.5 gigahertz frequencies. And then we have been trying to develop even smaller cavities for probing higher frequencies, and this is sort of the vacuum chamber for these. We don't need a very high vacuum or high pressure, so even a normal vacuum chamber is sufficient for our experiments. And then, so this is an electronics lab where you have some of the components. Then you have the simulation station, and we have LabVIEW and a couple of simulation software for doing simulations. And then I've been fortunate to have this lab with its own classroom. So I have sort of a board and this facility where teaching can be done. So the main purpose of this facility, where we have all these experiments, is basically detector development for particle physics experiments, and more than particle physics, because that requires even a bigger facility. So what we are trying to do here is, in my independent efforts, trying to develop instrumentation and devices or experiments which could someday help us have a tabletop experiment for like light, cold, dark matter detection, like axions or axion-like particles. Or we can have, like I've had a few studies here done which were involving the mesoscopic junctions to measure tunneling currents in mesoscopic junctions. So these have been kind of things that we have been doing here, and I'd like to acknowledge the support from Jazan University, which has been very kind in setting up this lab, initially from the physics department, and then later on from one of the national agencies in the Kingdom of Saudi Arabia, which has been the KAXT, King Abdulaziz City of Science and Technology, where I received a competitive grant, and that resulted in getting one of the highest precision and highest standard equipment for these studies. So if you have any questions.